All right, everybody. So let's talk about some linear kinetics. So we're going to begin to the kinetics part of the class. And I apologize. This presentation will probably be a little longer than I expected, and I wanted to, but I want to cover a nice broad base of the information you need to know, and then we'll spend some good time in class applying it to um, the athlete. But just a quick outline here for you. So we're going to talk about what the definition of force, the basics of Newton's three laws, types of forces, free body diagrams, and then we'll go into a little bit of the work and power concepts, which is a very big area now when we start dealing with athletes and human motion. But to define what kinetics are, at this point we're dealing with the identification of the cause of motion. So we're going to deal with the hand side of F equals ma, where before we were dealing with the right hand side. With kinetics, you do um, the outcome of motion, and this is now we're looking at what causes that motion to occur. So a simple definition of force is it's a push or pull that tends to cause motion, and I highlight tend here because the force does not have to cause change in motion. There's many things that have to occur in order for a force to cause a change in motion. Um, so it is a push or pull that tends to cause motion. There are numerous characteristics of a force. You'll see an individual here. Looks like they're getting ready to catch a pass or some sort of idea, but you'll have all these ideas focused on that diagram there to the right. But again, it's a vector, so therefore it has a magnitude and direction. And you'll see the vector in blue. So this is a very typical ground reaction vector that is an orientation towards the center of mass or center of gravity of the individual, and it is a magnitude of in the direction of where that impact is occurring. So the direction is usually towards the center of mass or center of gravity because that's where the ground reaction force is acting. And then the length of that blue line is the actual magnitude. Now the point of application, you'll see at some point on the ground where the interface and the interaction of the foot and the ground happens, and we usually call this center of pressure, is where it will happen. But that's where the point of application and the line of application is the extension of that vector, leading from the point of application towards the center of gravity or center of mass of the system. Um, and so here you have the newtons is what our force vector is going to be referred to, and that's just kilogram meters per second squared. So that's just basically taking the mass times the acceleration, and that equals the force. So going back to Newton and his Principia, so that's the original Italian title of what he's found. It's all in Italian. If you can find a original copy of this, good luck, have fun. And it's a pretty penny, but so it comes down to these three Newton's laws, right? So law of inertia, law of acceleration, and law of action reaction. So we're going to spend some time going in between these. What you do need to know is these are the three laws. Memorize these, know these in and out, know them in your own terms, um, and then know an equation that is associated with them, um, because you will need to explain these for the midterm. But we'll start with the law of inertia. And the law of inertia is Newton's first law. Um, and it deals with the object's tendency to resist motion, which is inertia. For a force to cause motion, the inertia of that object must be overcome, or the object remains in a current state of motion unless acted on by an outside force, right? So F equals ma, the motion is that mass times acceleration. In order for that to be changed, whether it is stationary or whether it is moving, there needs to be an external force that is applied to it. Um, that's why in outer space, because you don't have the gravitational pull, things go in a straight line or continue in a motion until something comes and bumps them into the other direction. So this is where that law of inertia is. Inertia is that initial inertial state or the innate state of you to resist any change in your current motion. And it's related to the mass of the object. So a greater mass has a greater inertia, a smaller mass has a smaller inertia. Also, a square or a block on the ground would also have a greater inertia as opposed to a same mass but a object of a round surface, right? Because now that surface area, you'll have to cause more force to move the block, um, possibly than you would with the circle or the sphere, because of the orientation and some of the characteristics there. So let's move on to the law of acceleration, which is Newton's second law. Now I've also put here law of momentum, and why I put that is because if you look at physics textbooks, and you take the physics class, the original creation of Newton's second law was in momentum terms. Um, and I'll show you in a moment how that is derived, but essentially the law of acceleration deals with F equals ma. Now what you're going to see is this epsilon here, and this is a summation of forces. So that is all the forces that are acting on the system. And what I mean by system is going to be apparent as we go further in this lecture, but it's important that you establish what the system is. And notice I'm not saying object, because there's a difference between an object and a system. And I hope to show you that a little later on in the lecture. But the summation of the forces acting upon the system cause the motion, and that's motion is ma. Now you'll see shortly where the momentum part comes in, but you can possibly think about it and just derive what a is if you want to think about it, why I'm going there. But an object's acceleration, so the a of this equation, is proportional to the resultant force in the same direction and inversely proportional to the mass. So just rearrange the equation and you can see where these two phrases come from. But now let's talk about the law of momentum. Well, if you take the sum of forces equals ma, you derive and expand out what a is. So it's mass times the change in velocity of the change in time. That right there is the momentum, mass times velocity. So now you have rho, which is representative of momentum. And so now you have the sum of forces equals the change in momentum over the change in time. And now we're going to move on to the final law, and that is the third law, and this is the law of action-reaction. Now I'm going to say a couple of terms here that I really want you to make sure that you are paying attention to, because this is a very important portion, and it's often kind of misunderstood. But for every force exerted by an object, there is an equal and opposite force exerted on the object. So those are two things. An exerted force by an object, there's an equal and opposite on the object. And that is simply written as the sum of forces of A on B equals an opposite but equal force by B on A. Right? So it's equal and opposite from one onto the other. And so this is how it's written. Sum of forces of A onto B is equal to the equal and opposite force of B onto A. Action-reaction. So if I push on the ground is going to push back on me with the equal and opposite force. That's what ground reaction force is. So now what I want to do is I want to go ahead and talk to you about different types of forces. And we're going to go over quite a bit of them just to kind of give you an idea on when you create a free body diagram where to look. This is not the totality of forces. This is just including a few of them that you see quite a bit in human motion. But the first one is non-contact forces, right? And so the most important one that we deal with on a general basis is the gravitational force. And so you see the center of gravity, and that's where it acts in the vertical against the system. But the force of gravity is inversely proportional to the square of the distance between the attracting objects and proportional to those of the product. And this is the equation you're going to deal here. So you have the sum of the gravitational force, and notice there's not the sum here, it's F, and that could be an F with a G, is the gravitational coefficient. And then M1 and M2 are the two masses. Now, this mass kind of gets this taken away when you, and so does the radius when you're talking about the gravitational pull towards the Earth, because the Earth's mass is so large and anything against it the radius is not big enough to make a difference. So they basically just draw that away, and so you'll just have that gravitational. It basically comes to one, and you have the gravitational one. So that's where you get gravitation. But the law of gravitation is a non-contact force, and it acts on the system as it pulls down from the center of mass or center of gravity. Now let's talk about contact forces. And the first one we're going to talk about is reaction forces, which is provided by surfaces, two surfaces, and generally one is moving or one wants to move. And that is a reaction force often is what you're going to deal with when it comes to human motion. You also deal with when you have a cyclist on a bike. If your system is the cyclist, then there's going to be some reactional forces in the interaction with the system and the bike, because it won't be the ground creating that reaction force. It will be the bike itself. But here we have, if you came into the lab, you'd see somebody running over a force plate, and it captures it in three directions, three dimensions. So you have an X, Y, and Z. You have the vertical, you have the anterior, posterior, and you have a medial lateral. And these are two typical walking and running. So the one on the left, A, is going to be a typical walking, and the one on the right, B, is going to be a typical running. You have the black line is the anterior posterior, so you'll see some braking, and we'll talk about this more in class. I'm propulsive. The blue is representative of the vertical, and that is going to be a representative of what's happening with the center of mass. So ground reaction forces are a response to the center of mass or center of gravity of the system. And we'll discuss that more in class as well. So another reaction force we're going to talk about is joint reaction forces. And what I mean by the summation of segments across a joint is, if I'm looking at the knee joint, the reaction force is created by the distal portion of the femur pushing against the proximal segment of the tibia, portion of the tibia. So those two combining together, those two surfaces are going to push together in whichever orientation they are to create a reaction force across the joints. Now, a big component of movement is friction. I will tell you, so this was the cause of a lot of discussion from my comps, but friction, it really causes us to be able to move across the surface. Think about somebody trying to walk across the ice skating rink, and maybe the lack of friction there, or slips and falls are often associated with friction. So when we create and develop shoes that are anti-slip, we're looking to increase the friction. But what is friction? Well, friction is the force acting parallel to some interfacing between two surfaces that are in contact. And again, so what you're going to see here is the same with tendon motion, but this is motion or impending motion of one surface as it moves over another. So there doesn't have to be any motion, but it has to be an impending or an attempted motion or a cause of motion. This frictional force is in proportion to the normal force, and that's a contact force. Normal force is the ground reaction force type of thing, but it's also a force of one object pushing on the other is the normal force between two surfaces. So it's the frictional force equals mu times n. So mu is the coefficient of friction, n is going to be the normal force, and then the F on sub F is the frictional force. Here's a little diagram of the traditional block. So what you'll see a lot of times is we're going to use this block just to kind of illustrate a few topics and a few conversations. And then you can transfer that to the human motion part, right? So if you look on the very top, it says direction of impending motion. So the block, say the block is just sitting there. There's no motion. Somebody comes along and pulls towards the right. So you'll see that pulling force. So we're going to pull it along this table surface. The weight of the block is the force due to gravity, right? So it's at the center of gravity of the block, and it's pushing it down. So there would be an equal and opposite blue vector going up if we were doing a diagram. But on the back, you'll see that frictional force. So it's going in the opposite direction of the pulling force or impending motion of that block. Now we'll talk about what has to happen in order for that block to move in a second here, but that is what's happening. So at this point, they're going to pull hard enough to where it starts to move, and so it no longer is impending motion, but motion happens, and the frictional force changes from a static to dynamic. We'll talk about that in a second. But here you go on the right-hand side. The coefficient of friction is the frictional force divided by the normal force, and that's how you determine your coefficient of friction. So the normal force would actually be that force that's equal and opposite the weight of the block. So that vector that's going back up, that's going to be your normal force. So you would divide the frictional force by that normal force. So in other terms, it's the vertical or the frictional force is the anterior posterior, and the normal force is going to be the vertical component of the force, and that's where you get your mu from. So I told you we were going to talk about static and friction force. So this is a diagram of what happens on the x-axis when you apply a force. So left to right is increase in application of force. Whether it's a push or a pull, it doesn't matter. And then on the y-axis, you have what the frictional force component is. You'll see two areas. You have static and dynamic. The static is, again, when the object is in pending motion. It's not moving, it's stationary, but you are increasing the applied force. Therefore, the static friction frictional force has to increase, but they are equal and opposite. So there's a linear relationship, right? At some point in that increasing application of force, movement happens. And at that peak, you have the maximum static coefficient of friction. Well, static friction, the static friction of force is less than or equal to the mu of static and the normal force, and the kinetic is equal to the kinetic mu and normal force. Now the dynamic is also termed kinetic, and that happens when you have motion. Now it may be surprising or not to you, but the maximum static friction that occurs is going to be greater than the dynamical friction. So once an object's moving, the friction that is created during that movement is going to be less than the maximum static friction created prior to movement. So what you're going to see here, there's a difference between like a translational friction and rotational friction. So rotational friction is going to be the resistance to rotation of a system. So we talk about the wheels, right? So what you're going to see in this diagram here, this is a kind of a introduction to what we're going to talk about in a second with free body diagrams. But if you look at that blue vector, tire pointing forward, that's the translational frictional force. So that's the interaction with the tire and the ground. But what you don't see here is if you talk about the bike and you talk about the tires, there's a rotational friction that is tending to cause resistance to that rotation motion of the cycle of the tires. Now think about what you think that may lead to, or what's causing that. There's brakes. There's the tension at the hub of the wheel between the how tight you make the screws. There's many components that are add to that resistant friction of the rotational friction. So when I talk about translation friction, I'm talking about the one occurring at the ground there with the blue one. But rotational is friction that's causing the wheels not to spin or rotate in an easily manner. So here just a little bit more. So rotational friction is resistant to rotation or twisting movement. Now let's go further into another one, and it's just a fluid resistance. And when I talk about fluid, I don't mean your general term of what you think a fluid is, like a drinking fluid or some kind of water or liquid. Fluid in this instance can be a gas or a water or a liquid. In general terms, we're talking about air and water for most of what we're going to be dealing with in class, but they both are part of the fluid resistance. When you talk about fluid dynamics from a physics perspective, this is what you're dealing with here. But in general, it has two basic properties that affect the motion, and that's going to be density, which is the mass per unit volume. And then you also have viscosity, which is the fluid's resistance to the flow. These both are going to affect how objects move through these fluids. Now, there are going to be two components that are taking from fluid resistance as as deals with human motion. The first is going to be a drag component. Now it's going to be parallel to the direction of motion in the opposite direction. So this is a portion component that is causing you to slow down, or not necessarily causing you to slow down, but tending to cause you to slow down, right? So its attempt is to make you slow down. And then you also have a lift component. Now, if we look at the equation for drag, we can find out where that want or that imposing area to reduce that speed comes from. So here's your force of drag equals 1/2 the coefficient of drag, so everything has a coefficient of drag, times the frontal surface area. Now this is the area or portion of this equation that the aero bars that we saw in class and in the positioning of a cyclist on the front handlebars with that one study we talked about, this is where they're attacking. So they're trying to reduce that frontal area by putting you in a more aerodynamic position to reduce that drag component, the air resistance. And then you also have rho. Rho is the fluid viscosity, so you'll know whatever the fluid viscosity is of the fluid around you. So whether it's the air or whether it's salt water or whether it's a lake or river. And then you have the relative velocity of the object. So this v squared, because the velocity of the object can either make things more turbulent or not. You start dealing with laminar flow or some of the other kind of flows. We're not going to get into that too much in this class, but if you want, you can spend a little time and go back and look at that. But to get into the lift force, it's perpendicular to the direction of motion as well as the force component. But it's interesting to note that lift only occurs if the object is spinning or if it's not perfectly symmetrical in that frontal area. So lift is produced by any break in symmetry of the airflow over the object, and that's why you have the airplane wings the way they are, because they're creating a lesser dense air motion above the wing and more dense below, so it's causing a lift in the airplane. But when we talk about our swimming, the lift component is buoyancy, and that's the term we use when we discuss swimming. And there's a reason why wetsuits are allowed and wetsuits aren't allowed, and it's because it depends on what the buoyancy of that. It's easier to swim with the less of your body submerged into water. So your drag is reduced with less of your body in the water. So this is an area where they come into play. So I've added a couple extras on here that we're not going to spend some time going over. Inertial, muscle, and elastic forces. These are all components within the body that are different mechanisms that cause motion in the human body. You can go in and look in the textbook if you want to find out what those are, and we may go into them a little bit here. But when we talk about our free body diagrams, we're not going to include these because these are all internal forces. And when your free body diagram, I want you to focus on external forces. And that's what you see here. The free body diagram, it's basically a stick figure representation of your system. The important thing is that we define our system and we only use the external forces. So it's not muscle forces, it's not the elastic forces of the tendons or whatever you want to portray this as. It's only external, okay? And those are the ones that we spent some time going over. But to create these free body diagrams, you essentially take your system, your item, and this is going to be a very simple system to start. And this is just a runner. So it's one person running. And we'll say that that foot in front is contacting the ground. So if I draw these, I would draw just 4 arrows. I would draw them as a stick figure. Or you would take the image like I have it here, and you draw the 4 vectors. So I have 4 vectors coming here. 2 used to go in the same way. That's only because we can't really know what motion's happening right now, or the reason I have the frictional force the way it is because where the center of mass is, I know that the anterior posterior ground reaction force is negative, and that's why I have that vector going that way. But you'll find out about that in a second. More in class, we'll talk about that. But when we do this, it's important that you give them all a turn in a writing. I'm not going to do it in this lecture, but in class we're going to go over on how we summate these and how we use them to describe the motion and to calculate the motion. Um, but so I have the F sub BW, and that's my body weight. So you generally see me refer to this as a BW, and that's my force of gravity. And then you have the ground reaction force split up in two, and that's the FGRFZ, which is the vertical component, and the FGRFY, and that's the anterior posterior component. Now, keep in mind the reason I do this is because the true ground reaction force vector is going to be going from the point application of the foot hitting the ground back towards where that center of mass is. So it's going to be at an angle. And so you have to decompose that resultant vector into the components of the z and the y. Here you don't see that because of my ground reaction. The way I write my free body diagrams, I go ahead and separate them right away. And then he's moving from left to right on the screen, so the air resistance is going to be going in the opposite direction, so you have it there. Now keep in mind that the FBW and the FGRFZ, those should be equal and opposite. So just keep that in mind on how we go. And the force of gravity and force of body always goes just straight down vertically. So now what I want to do is do the more complicated system and how we would use and define systems. But so for this point, I have a cyclist and a bike. And what I want to do here is I want the bike and the rider to be one system. So don't imagine they're separate. Imagine that they're glued together and it represents one system. So now I want you to go ahead and think about how you would represent that as a free body diagram if he's going left to right. And what I mean by that is think about, first you got to think about the force of gravity and think about all the different forces acting on the system, and then how you would create those as a representation of a free body diagram. So how many force vectors do you need to draw? Well, the easy one is always going to start with just the force of the body weight. So that's going to be from the center of gravity of the entire system straight vertical towards the ground. But here's where it gets tricky, right? So there's two contact points with the ground. So we have to make up the components of the ground reaction force into both contact points, because each of them is going to return a portion of the force. Now, if the positioning of the body was equal, and they were both, so we're going to, in this case, we're going to say they're both the same length. So the summation of those two GRFZ forces should equal and be opposite the force of the body weight. And we're going to talk about this in class a little bit. So we'll do a different formation, but we'll do it in class. Then you also have the frictional forces. Now, there's going to be a frictional force in each of the contact points as well. Now think about why I have the frictional forces going the way they are. I'm going to ask you that in class, so make sure you understand and you spend some time thinking about it, because that's going to be one of the questions I ask in classes. Why did I draw my frictional forces going forward when the motion of the person is also going forward? Okay, so think about that, come with the answer to class, and we'll discuss as well. But there's at least one more force that we're going to talk about here, and that's air resistance. If he's going left to right, there's got to be air resistance. And remember, air resistance is actually a fluid. So this is going to be a free body diagram of the bike and the rider as one system. And we'll talk about how you take those and create the equations of motion from this. So now I want to go further and talk about some relationships and some other concepts that we deal with the kinetics and in describing motion. And the first one is going to be the impulse-momentum relationship. But we'll first define what impulse is, and that's just the force applied over a period of time. And it's represented by the area under a force-time curve. So when I apply a force, there's a certain period of time I apply it for, and it looks like this. So on the y-axis, you have the force application. On the x-axis, you have the time I've applied it for. Now, what this is representative of a vertical ground reaction force during a counter movement jump. So the blue line represents the motion of the body, the center mass relative to it. After 1.5 seconds, he's aerial, so there should be no recorded ground reaction force. So to calculate the impulse, you take the area under the curve, and that is you make small little segments, and you just calculate force times time delta t for each of those. You'll see this separated by body weight impulse and jump impulse. We'll talk about that in class 2, so I can describe that a little bit better for you. But by dividing those, by taking those two chunks, we can talk about how much impulse it took to create the jump. And that's a way we do some measurements of fatigue as well as performance. We measure this to identify that. The units are Newton seconds. Think about forces in newtons, and then we're doing time, so seconds. So there you have your Newton seconds. And then momentum. Going back to momentum, represented by the rho. Momentum is the movement of the massive system, so it describes that velocity of the system. It's kilograms per meters per second. And so if we go ahead and go back to F equals ma, break it down again to F equals mass times delta V over delta T, we rearrange the equation. So now we have on the left-hand side force times time, and on the right-hand side we have mass times velocity. That equals impulse on the left and momentum on the right. So this is how you break that down, deriving it from F equals ma. So the impulse is the measure that is needed to change the motion of or the momentum of the object. So now let's talk about some mechanical work, and we call it mechanical work because we're only really worried about the mechanics of it and from biomechanics perspective. But it's the effects of force application over the distance. So it's that how far an object moves with the force application. So work equals force, which is also the cosine of that angle of the force application to the object. And S is the distance of displacement. So if you go back to the way the book does it, so for me I usually use that as a D, not a S, but it's the displacement from point A to point B. So the units are Newton meters or joules. And this is going back to the block concept, right? So this is a pushing force directly towards it. So at this one, it would just be F times S because the cosine of theta of 90 degrees. You don't worry about it. It's just going to be straight on. It's going to be a 1. So force times S is if you are pushing force or pulling force is in the direction of motion. Now, if I'm pushing at an angle or pulling at an angle, this is where you would include that cosine of theta from the direction of push to the motion of the system. So this is where you can come into play with trying to figure out whether it's more effective to push or pull, or push from a certain angle and pull from a certain angle, and you would use this equation. Taking work to the next step is power. Power is a very hot topic, and this is what they use for power meters in cycling, and now they're creating power as a measure for running. But it's the amount of work done over time. So a more powerful athlete can produce the same amount of work in a shorter period of time. So a metric of improvement from a weightlifting and performance perspective is that somebody can do the same work in a shorter period of time or become more powerful. So you have P, which is a capital P equals power, is delta W over delta T. Now this is in watts, which is joules per second. Now what I've done here below is I've went ahead and derived this equation to show you how people are actually using it as a measure and how they use it in pedals in cycling to do power, and it's force times velocity. So the velocity of movement and the force of the pedal is going to be how they do it. As well as running, they're talking about velocity and force. Running, there's still some questions on whether it's accurate, but in cycling, they've had some pretty good numbers, and people use power as a measure quite often, and it's getting some good results. So the last one we're going to talk about is mechanical energy, and energy is the capacity to do work. But from mechanical energy perspective, there's three that we're going to talk about. Two that we use mostly, but we'll discuss all three of them. The first is kinetic energy, and what that is the result from motion. The equation would be 1/2 mv squared. We have potential energy, so this is the capacity of something to do work. And that equation is mgh, which is mass times gravity times height. And the third and final is strain energy. Strain energy is elastic energy that is stored, potential energy, and then released following deformation. Strain energy comes into play a lot with running. You consider during ground contact time some strain energy in the system, and especially in the ligaments and tendons and some muscles, and you're going to rebound and restore that strain energy during push off of the system. So strain energy comes into play a lot there, and so it's 1/2 K, which is a spring constant, times a delta X, a change in position or change in length of the spring system, squared. So this goes a lot off Bernoulli's principles and some other components of mass spring models that you will deal with. We'll talk a little bit about it in the class, but I've had some decent work. I try to identify mass spring models and simplifying human motion into a mass spring system. But this all leads us to the law of conservation of energy, which is energy cannot be destroyed nor created. So you have the total energy of a system is comprised of what the potential energy and the kinetic energy. So we'll go back to the general idea. So potential energy is maximum at the highest point relative to the ground. Kinetic energy, again, at that point would be 0. And then as the system falls toward the downward flight, it changes energy to kinetic potential energy. So right before contact with the ground, kinetic energy is at the maximum, potential energy is at 0. So as you go from high to low, potential energy decreases, kinetic energy increases, and the opposite as you go into the upward flight. So as you develop, so think about projectile motion, as you develop towards your apex of flight of motion, your potential energy is increasing. As I stand on a ladder, my potential energy is the greatest. My kinetic energy is 0, but if I fall off the ladder, it switches. So those are the kind of concepts you have with potential kinetic energy, and we'll use those to our advantage throughout the class as well. So sorry, this one was a little longer than expected, but go ahead and take the quiz, and we'll come to class and spend some good amount of time discussing the topics we talked in from a perspective. Please come with your questions and make sure you look at that frictional component, the cyclist, and come with a response. So I'm looking for a couple people to tell me about that. All right, thanks guys.